So hi, I'm Oren from Carnegie Mellon, from the Robotics Institute. The problem is motivated by HRI, human-robot interaction. And I think the algorithmic community can get a lot of interesting problems from that community, and there's not enough collaboration there. So I'm going to make, the problem I'm going to talk about is planning in the presence of risk regions. I'm going to motivate it using this example. We have a user with disabilities, and he needs to perform some task. In this case, it's going to be pouring water from the pitcher using a robotic arm. And we have two different types of configurations here in this problem. Configurations, which we can see on the top, where both the end effector and the pitcher are visible to the user, and configurations where they're not visible to the user. And we want to plan paths which are as visible as possible, but we don't want to exclude paths where the end effector is not visible. So we call these lower configurations risk regions. In the 2D case, which is another example here, we have some kind of a threat. In this case, it's a sniper, say, in the middle. And there's all points visible to the sniper, which define a risk region. This is the purple region. And we want to plan a path between a source and a goal point. And we want to balance two properties. We want to minimize path length, and we want to minimize exposure to the risk. And this is key, that we want to minimize that consecutive accumulative exposure should be penalized in a superlinear fashion. So what does it mean? 10 seconds of exposure to the threat is much worse than 10 one-second exposure intervals, right? So we call this problem risk-aware motion planning, and it's surprisingly similar to a talk that we had about risk-aware, but it's not the same thing. And we want to define a cost function that simultaneously balances path length and exposure, and then plan a minimal cost path. I'm going to define such a cost function, and it's not that hard. I'm going to use the assumption that the robot moves at constant speed, so you can talk about path length and path duration interchangeably. Then we need one more notation, which is the current exposure time. This is simply the time passed since the robot entered the risk region. So we have the figure on the top there, where the path gamma passes between the safe region, and then it enters the risk region, and then goes back to the safe region. And then the current exposure time is 0 when we're in the safe region. It starts to grow linearly when we enter the risk region, and drops down to 0 when we return back to the safe region. And now the cost function, which is key here, is we integrate over the path, and at each point, we take e to the power of the current exposure time. And the exponent here is not important. You need to take any superlinear cost function. So when the current exposure time is 0, so e to the power of 0 is 1, and we simply get path length. And this is depicted in the lower part of the figure, where the path grows linearly when we're in the safe region. When we enter the risk region, we get an exponential penalty, and we can see that in the superlinear part in the risk region. Once we exit the risk region, we return to grow in a linear fashion. So now we can formally define the problem. We're given free space, which constitute of a safe region and a risk region, and some obstacle region. We want to plan a path between a source and a goal. And I'm only interested here in planning in the plane. So if you go to higher dimension, obviously this is a generalization of the motion planning problem, and it's hard. And this figure here gives some visualization of the cost function. So this is motivated by early sailing, where sailing across coastal lines was considered safe. So the white regions next to the land masses are the safe region. The open waters, which was considered to be risky, are the risk region. So if we want to minimize only risk, namely go as much as possible, avoiding the open waters as much as possible, then this is the red path that tries to be always within the white region. And we can see that it's very long. If we want to take the shortest path, which ignores the risk region, that's the green path. And using our function, we have some kind of balancing between this risk and shortest path. So now I can define the open problem finally. So the problem is this motion planning problem in the plane computationally hard. And this can be either hard due to the algebraic complexity or the combinatorial complexity of the problem. And assuming that it is, which is what we conjecture, can we find an efficient approximation algorithm for the problem? And I formally defined everything with all the math in a recent we uploaded it to archive. And I want to make a few small comments on the problem. So first of all, as I said, the general problem is p-space hard. So that's why we limit ourselves here to the planar case. If we look at the discrete case, where we have some kind of a roadmap, then you can solve it efficiently. You can apply Dijkstra as is to the problem, optimizing over this cost function. But with some modification of Dijkstra, you can solve this pretty easily in polynomial time. Some more work which are closely related here. So the cost function that we proposed here actually originated from a problem that Ure had 10 years ago in Wafer. The 2008 is their journal version of the problem, where they balanced path length and path clearance. And their cost function was integrating over the path and at each point taking 1 over the clearance. And although the path is not known, the problem, we don't know if it's hard or not, but we have a p-task for that problem. So we can get a 1 plus epsilon approximation for any epsilon. So in that sense, this is very encouraging. On the bad side, another problem which is closely related is planning for weighted region shortest path, where we have this planar subdivision, and the cost of a path is the weighted sum of Euclidean paths. And here, under a reasonable model of computation, the problem cannot be solved. So the question, again, that I'm asking here, is this problem computationally hard? And if it is, can we get an approximation algorithm for the problem?
All right, thank you. Thank you. Does it work? Thank you.
OK.
Hey, can you go back to slide number 2? I have a couple of questions about your open problem. I'm sure the audience may have some. No, one further, sorry. Yeah, this one, right? If you look at the top right problem, if you just only wish to minimize exposure, like in terms of the length of the exposure, regardless of how long the path is that a problem open?
So if you only want to minimize exposure.
Yeah, so in the top right is a perfect example, right? You have the purple region, that is exposure, and you have a start and a goal, and I want to find the shortest, no, not the shortest, but a path that minimizes the intersection. So just to keep it simple, like right, is that problem or still open?
So if you have polygonal obstacles, my guess is that you can get, that's a good question. Sorry? I'm trying to think out loud. My guess is that it's not, because you don't get a weighted region. Basically, it's like the weighted region problem where you have a weight of 0 within the safe region and a weight of 1 within the risk region, right? So I think basically you're asking, you can go for free within any point in the safe region. And
yes, exactly. So I think if you have an open problem, you try to strip it down to the simplest subversion of it that you want to see. Hey, can I solve that? Right?
I think we can solve it. I can't.
0, 1, infinity.
Yeah.
Mitchell has results on that as well, so which is easier than
the general weighted problem. Okay, so that's an approach.